In February 2022, an attacker minted 120,000 wrapped Ether worth $325 million completely out of thin air. They never deposited a cent. They just convinced a bridge that a deposit had happened. This is the Wormhole hack, and it comes down to a single broken check. Today we rebuild that exact mechanism in Foundry, run the attack ourselves, and see the real exploiter on chain. Wormhole is a bridge connecting Ethereum and Solana. The idea is simple. You lock real Ether on one side and the bridge mints you a wrapped copy on the other back to one-to-one. But how does the far side know a deposit really happened? It trusts a group of off-chain watchers called Guardians. They see your deposit and they sign a message attesting to it. Show the bridge enough of those signatures and it mints the wrapped tokens. So the whole system rests on one thing, those signatures being real. Here is the flow. You deposit Ether on Ethereum, the Guardians observe it and produce a signed message. In Wormhole's world, it's called a VAA, a Verified Action Approval. That signed message is handed to the bridge on the other side, which checks the signatures and, if they're valid, mints your wrapped Ether. Wormhole used 19 Guardians and needed 13 of their signatures to accept a message. That signature check is the entire security of the bridge. So what happens if the check itself is broken? This is the heart of it. To be safer, the bridge must check those signatures against its own fixed list of real Guardians. Wormhole's check instead trusted an input the caller could control. In the real hack, it was a spoofed system account. The effect was that the attacker could point the verification at their own keys. So they signed a fake deposit with keys they controlled, called those keys the Guardians, and the bridge believed them. It minted 120,000 wrapped Ether, backed by absolutely nothing. And it's all right here on chain. This is the attacker's address on Etherscan, labeled in black and white Wormhole Network Exploiter. The red banner warns you directly. This address is involved in the Wormhole Network exploit. You can even see where the funds were first sourced. Tornado Cash, $325 million, conjured from a single check that trusted the wrong list. Now let's rebuild the check ourselves. We've written a minimal version of this bridge in Foundry, the standard Ethereum toolkit, and we'll run it left. 3 acts. First, the honest case. Real Guardians sign a genuine deposit and the bridge mints correctly, then the attack. An attacker signs with their own keys, calls them Guardians, and mints a fortune out of nothing. And finally the fix, the one change that shuts the whole thing down. Let's open the code. This is the vulnerable bridge in VS Code. Let's be precise about what these signatures actually are, because that's the whole game. To approve a withdrawal, a Guardian takes his details, who gets paid, how much, and a nonce, and hashes them into a single fingerprint, here called the digest. Then it signs that digest with its private key, producing a 65-byte signature. The SIGs array is just a bundle of those. Now watch the check. For each signature, this recover function takes the digest and the signature and returns the address that produced it. It works out who signed. And here's the trap. Recover always returns some valid address, it never fails. So the only real question left is that signer a Guardian? And it checks against claimed Guardians, a list passed in by whoever called the function. The caller hands over both the signatures and the list they are judged against. So an attacker signs with their own keys, passes their own addresses in as the Guardians, and every single check passes. Before we run anything, let's read the test. Act 1, the honest case. We deployed the bridge with the real Guardian set. Then we built a genuine withdrawal, 10 wrapped Ether to a user, and this helper, sign, takes its digest and signs it with each real Guardian's key. That's literally what producing a signature is. We pass in the real Guardian list and those real signatures. Call mint and assert the user actually received their 10, the bridge working exactly as intended on real attestations. Let's run it right in the terminal. First, the honest case. Real Guardians sign a genuine deposit for 10 wrapped Ether and the bridge mints exactly 10 to the user. It passes in green exactly as designed. This is the system working correctly when the signatures really do come from the Guardians. Now the attack test. And notice how little changes. Same bridge, same withdrawal digest. But this time, the sign helper uses the attacker's own keys, not the Guardians, and the crucial part, we passed the attacker's own addresses in as the Guardian list. We mint 120,000 wrapped Ether to the attacker, backed by no deposit at all, and assert their balance really is that. The signatures are perfectly valid, they just come from the attacker's keys, checked against the attacker's list. If this passes, the bridge minted a fortune from forged attestations. Let's run it and watch. Now the attack. Same function, but this time the attacker signs with their own two keys and passes those same two addresses in as the Guardians. Watch the number. The bridge mints them 120,000 wrapped Ether out of nothing. No deposit, no collateral, and every signature is technically valid, they're just not from the real Guardians. The bridge had no way to know the difference. That's the $325 million bug reproduced in front of you. And here's the fix, and I've put the whole difference in a comment right at the top so you can see it side by side. Before, the function took a claimedGuardians argument, a list the caller handed in, and checked the signatures against that. After that argument is gone completely, the check now uses Guardians. The list the contract stored once at deployment that nobody calling in can change. Same signatures, same recover, but now they are measured against the real Guardians instead of a list the attacker gets to write. That is the entire fix, one word. claimedGuardians becomes Guardians, and the caller loses all control over who counts as a Guardian. And the fix tested. Exact same attacker, exact same forged signatures, but now we point them at the fixed bridge, the one that checks against its own stored Guardians. We tell the test to expect a revert, with the reason not a Guardian, and then we assert that nothing was minted. The attacker's balance stays at 0. This is the proof that that one line change actually kills the attack. Let's run it. And we prove it. Same attacker, same forged signatures, but now against the fixed bridge. It reverts, not a Guardian, nothing is minted. The exact attack that conjured $325 million a moment ago is now completely dead, stopped by pinning the signature check to the real Guardians and refusing to trust a list the caller supplies. So what do we take from Wormhole? That verifying a signature is only half the job, what you verify it against is the other half, and the more important one. The attacker's signatures were perfectly valid, they just came from the wrong keys. The fix was to pin the trusted set into the contract itself, immutable, and never accepted from whoever is calling. Anytime a contract checks a trust against data an attacker can supply, that's not security, it's a suggestion. Quick recap, Wormhole minted wrapped tokens whenever it saw enough Guardian signatures, but its check trusted a Guardian list the caller supplied, so an attacker signed with their own keys and minted 120,000 wrapped Ether from nothing, $325 million. We rebuilt that exact bug and watched it happen, then fixed it with one change, verify against the real stored Guardians, and the identical attack simply reverts. If taking real hacks apart and rebuilding them in code you can run is your thing, that's this whole channel. These take real work to make. If it helped, the wallet's on screen and there's a Ko-fi link below. Every bit fund the next breakdown. Thank you. That's the anatomy of the Wormhole hack. Not a broken cryptographic signature, but a signature checked against the wrong list, rebuilt and defended right in front of you. If you want more of these, we take apart a real hack every day. Subscribe, comment the one you want next, and I'll see you in the next breakdown.